picture the scenario, if you would. It is 3 a.m. and your phone is just screaming on the nightstand.
Oh, yeah. The absolute classic nightmare for anyone in tech.
Right. It is the worst. A critical service in your infrastructure is failing under real-world load. So you jump on the emergency incident bridge, you wipe the sleep out of your eyes, and pull up the monitoring dashboard.
And let me guess, the latency graphs look like a hockey stick pointing straight up.
Exactly. Straight up. So you do what you always do, right? You open up the source code to figure out exactly what is breaking. But here is the massive catch. Nobody on that incident bridge actually wrote this code.
Which is terrifying. I mean, historically, if you were staring at a critical system and nobody present had authored it, it meant the original developer had, quit the company.
Yeah, they moved on.
But today,
Yeah.
it increasingly means the author was never a person to begin with.
It's wild to even think about. But that profound lack of understanding is exactly what we are digging into for you today. We are exploring this brilliant piece of source material called Nobody Pages the Agent.
It's such a great title.
It really is. And our mission for this deep dive is to understand why agent-generated code creates this highly dangerous phenomenon known as comprehension debt for human responders.
Yeah, we really need to get into why this happens, why it is so incredibly risky, and how we have to radically change our operational standards to survive it.
Okay, let's unpack this, because the way the tech industry currently thinks about software development seems to have this massive, just glaring blind spot regarding what happens after code actually goes live.
Well, to understand that blind spot, you really have to look at the modern software development lifecycle. Right now, the industry is just completely fixated on the pipeline itself.
The shipping part.
Exactly.
Yeah.
Engineering organizations are obsessed with this journey of, getting code specified, drafted by an AI agent, passed through automated testing, and merged safely into the main branch.
Right. It's all about speed. Clear the testing gates as fast as humanly possible.
Yes.
Yeah.
But the diagram we draw of this whole process, it ends way too early. The pipeline stops the exact moment the code is deployed. But the service itself, it lives on, it operates, it scales, and eventually it degrades.
Yeah, the moment of deployment is really just the birth of the software. The actual life cycle is everything that happens afterward in the real world.
Precisely. And crucially, when that service breaks in the middle of the night, nobody pages the AI agent.
Right.
The model that wrote the code does not carry a pager. It doesn't, join the Slack huddle to troubleshoot with you. Every single system running in production still requires a human owner.
But just having your name listed as the owner of a service in some corporate catalog, without possessing an actual deep understanding of how that system functions, that's functionally useless during an outage.
It is. It's just a name on a page.
So let's talk about the specific kind of code that actually causes these 3 a.m. nightmares. Because, when we criticize AI-generated code, we aren't talking about obvious syntax errors.
Oh, definitely not.
Right, like if an AI forgets a semicolon or uses the wrong variable type, or just hallucinates a library that doesn't even exist, the compiler catches it instantly.
Yeah, the build just fails. It never even gets close to production.
Exactly. The real danger lies in the invisible failures.
And this is where the source material introduces a really phenomenal concept. They call it the confident defect.
The confident defect. I love that term.
It's so accurate. A confident defect is a failure that ships fluently, meaning the code diff looks perfectly clean and logical to a human reviewer.
It looks like good code.
Right. And all the automated unit tests pass with flying colors. The AI agent cleared every single gate you put in front of it. But the completely wrong thing still reaches production because, the defect exists in a blind spot.
If I think about a standard retry policy, I can see exactly how this happens in the real world.
Oh, that's the perfect example. Walk us through it.
Okay, so let's say you prompt an AI agent to write a service that pulls data from an external database. You tell it, hey, if the database returns an error, retry the connection up to 4 times.
Sounds pretty standard.
Right. And the AI writes this highly elegant loop that does exactly that. It even writes unit tests to prove it. So in the test environment, the database is mocked to return a 500 internal server error. The code retries 4 times, and the test passes.
Merges fluently.
Exactly. It sails right through.
Yeah.
But out in the wild, out in live production, databases don't always politely return a clean error code. Sometimes they just get incredibly slow.
Yeah, and that slow dependency completely bypasses the logic of that pristine test you just wrote. The database isn't dead, it is just struggling to keep up.
Right, it's gasping for air.
Exactly. So your AI written service hits a timeout threshold, assumes an error occurred, and triggers the retry. But because the database is merely slow, those new retry requests just pile right on top of the original still processing requests.
Oh, wow, so it just compounds the problem.
Exponentially. The load amplifies. More requests come in from real users, more timeouts happen, more automated retries are fired off, and within seconds, I mean literally seconds, a minor database slowdown spirals into a massive thundering herd problem that takes down your entire infrastructure.
That is wild. It's like a car crash test.
Okay, how so?
Like, you can engineer a vehicle that scores a perfect safety rating in a sterile, highly predictable testing facility, right? It hits the concrete wall at exactly 35 miles per hour, the sensors trigger, the airbags deploy perfectly, and it gets 5 stars.
Right. On paper, it is the safest car in the world.
Exactly. But then the steering column completely locks up the moment the car encounters, an unexpected pothole on a real highway. A testing gate only catches what its standards are explicitly designed to exercise.
That's spot on.
The AI agent did absolutely everything the specification asked it to do. But the simplified system described in those tests, that is not the complex, messy system that triggers the pager at 3 a.m.
What's fascinating here is that, AI agents did not invent the confident defect. I mean, the human engineers have been writing code that inadvertently causes thundering herds for decades.
Oh, for sure. We are very good at breaking things.
Right. But what AI agents did was radically change the economics and the velocity of these failures. They just pump out these plausible, highly fluent, but contextually incomplete implementations at a speed that is really difficult to comprehend.
They just generate code way faster than human teams can possibly spot what the original model omitted.
Exactly. And because these defects are functionally guaranteed to reach production at hyperspeed, the human tasked with fixing them is just put in an impossible position.
Which brings us to this critical term coined by Adi Osmani, which the author of our source material highlights, and that is comprehension debt.
Yes. Comprehension debt.
We are all pretty familiar with technical debt, right? Like, that is a conscious choice. You take out a loan, you write messy code, or take a shortcut to ship a feature by Friday, knowing full well you have to pay it back by refactoring it later.
Technical debt lives entirely in the code base.
Right. But comprehension debt is entirely different. It lives in the distance between the complexity of the system itself and the mental map of the people responsible for restoring it.
It is the gap between what the system actually does and what you understand it does. And as you mentioned, you aren't taking out a conscious loan here.
No, not at all.
You are just waking up one morning to find that you are responsible for this sprawling architecture you don't even recognize.
I do have to challenge this premise just a bit, though.
Okay, go for it.
Because, inheriting code you don't understand isn't really a new phenomenon. Developers have always had to maintain legacy systems. You join a new company, someone points you to a 10-year-old monolithic code base written by 5 people who left years ago, and you just have to figure it out.
Oh, absolutely.
So why is an AI-generated code base inherently more dangerous than, a traditional legacy code base?
It is the most common objection to this entire argument, and it is totally fair. Human authorship never guaranteed shared understanding. Just because a person wrote it didn't mean the rest of the team understood it.
Right.
But here's the fundamental difference. Human authorship necessitated a process that created repeated chances to build that understanding. It provided friction. In the context of building a mental map of a complex system, friction is actually a feature.
Wait, I really like that. Friction is a feature. If I compare it to, physical navigation, it is the GPS effect.
The GPS effect.
Yeah. If you use a GPS app to drive around a new city for 3 years, you successfully reach your destination every single time. The technology works flawlessly. But the day your phone battery dies, you suddenly realize you have zero mental map of your own neighborhood.
Because you never had to pay attention.
Exactly. You never had to struggle to find a landmark or take a wrong turn or actively memorize a street name. The friction of getting lost is what actually builds the map in your brain.
That is a perfect analogy. Historically, shared understanding of a software system was forged in that implementation struggle. It was built during heated design arguments at a whiteboard.
Oh, yeah, those hours arguing over architecture.
Right. It was built in pull request comments, going back and forth between peers, arguing over edge cases. It is knowing that you can just message a teammate who remembers exactly why the retry count is set to 4 instead of 5.
Because they spent 3 days agonizing over an API rate limit.
Exactly. AI agents completely compress or just eliminate those human encounters. They remove the friction of discovery.
But, I mean, the AI does leave a trail, right? The source material specifically mentions provenance. We aren't completely blind here.
Sure, you get a transcript.
Right, you get a full transcript of the prompts the developer gave the AI, the code the agent suggested, and the exact timestamp of the human clicking accept. Doesn't that historical log count for something during an outage?
A transcript is just a log of what an agent attempted and a human accepted. A transcript is not a mental model.
It's just a receipt.
Basically, yeah. When you are on that bridge at 3 a.m., under immense pressure, with thousands of users experiencing errors and revenue dropping by the second, you do not have the time, or honestly, the cognitive capacity, to sit and read a 50-page chat transcript between a developer and an LLM.
No, nobody's doing that.
You need a much smaller, highly specific operational map in your head. Like, what does normal look like? How does this specific system fail? And what is the exact mechanism to return it to safety?
And when you are generating code at what the author calls merge speed using AI, you aren't building that map. You are just aggressively accumulating comprehension debt.
Yes.
So when the pager goes off, you are starting entirely from symptoms in the dark with absolutely no internal compass. If you are managing a team of developers right now, you might be celebrating how fast your AI tools are shipping features. But what this actually means is that you are setting your incident responders up for absolute failure.
Which forces us to confront the core operational dilemma here. If we are generating code far too fast to understand it and acquiring all this comprehension debt, how do we possibly pay it down before the pager ever goes off?
Because telling developers to simply, read the AI's code more carefully during review, that is a fantasy. It just doesn't scale. So what is the actual mechanism to survive this?
The author's primary solution is really profound, and it requires a complete shift in how we define a specification in the first place. Operability must become a hard requirement baked directly into the spec itself.
Okay, meaning what exactly?
Well, if a developer's intent compiles into implementation via an AI, then the ability for a human to actually manage and recover the system has to become part of that initial intent.
Meaning you don't just prompt the AI to build the feature, you require the AI to simultaneously build the safety and recovery mechanisms for that feature.
Yes, but with a massive caveat that teams get wrong all the time. An AI agent can absolutely draft a runbook for you.
Sure, they're great at that.
Right? It can spit out a beautiful, well-formatted markdown document explaining step-by-step how to troubleshoot the service it just wrote. But a generated runbook is just, as the author brilliantly terms it, generated confidence.
Generated confidence.
Yeah, it is a theoretical artifact that states what should happen in an emergency. Generating confidence is easy. What we actually need is proof.
Here is where the methodology gets really interesting. The text brings up chaos engineering, but instead of running chaos experiments in production, which, let's be honest, is terrifying for most companies.
Well, absolutely terrifying.
It shifts the chaos directly to the deployment gate. You don't just let the AI write a rollback path and assume it works. You force the testing pipeline to actually execute the rollback, inject artificial latency into the database, and verify that the monitoring alert actually fires. And you do all of this before the code is ever allowed to merge into the main branch.
Exactly. You are mechanically proving that the system can be operated by a human before it is allowed to exist in production.
That is such a powerful shift.
It really is. And to formalize this, the author lays out a specific minimum service contract. This is the absolute baseline operational proof required for any AI-assisted service to merge.
Let's actually dig into the mechanics of that contract, because this is where the theory hits reality. The first requirement is having a defined SLI, an SLO target, and an implied error budget.
Right, the absolute basics.
Yeah, for anyone listening who hasn't stared at a site reliability dashboard lately, an SLI is just the metric you track, like response time. The SLO is your target, say 99% of requests finish in under 200 milliseconds.
Yep.
And the error budget is essentially your acceptable allowance for failure. If your AI-generated service burns through that allowance, it is mechanically proven to be unreliable.
That is the foundation. You have to measure user impact. Now, the second requirement is a named, accountable owner and a clear escalation path. A real human who is ultimately responsible when the machine fails.
Makes total sense.
But the third point is where it gets highly specific to the AI failures we discussed earlier. The service must have defined proven behavior for critical dependencies when they are slow, not just when they're failing outright.
The thundering herd prevention. So you have to prove the code won't retry itself into oblivion when the database lags.
Precisely. The pipeline has to inject latency and prove the system handles it gracefully. Then the fourth requirement is an actually executed rollback path, not a described one in a document.
Right, not just words.
The deployment pipeline itself has to deploy the change, and then prove it can undo the change automatically and restore the previous state without data corruption.
Which moves us to the runbook. The contract demands a shipped runbook for high-impact failures. But it can't just be a generic troubleshooting guide, right? It must include the specific signal that identifies the failure and the exact first safe action a responder should take at 3 a.m. to stop the bleeding.
And finally, the contract requires defined behavior for saturation.
What happens when it's overloaded?
Exactly. What physically happens when the system gets overwhelmed with traffic? Does it degrade gracefully by turning off non-essential features? Does it actively reject new work and drop packets? Or does it completely fail, close, and crash?
An AI will typically write the simplest code, which usually means it doesn't handle saturation at all.
Exactly. You have to force it to prove its saturation behavior.
Now, looking at this contract, anyone listening with a background in site reliability engineering is probably nodding along right now, but also rolling their eyes.
It's because none of this is new.
Right, none of this is actually new. SREs have been begging developers to define saturation limits and write rollback runbooks for a decade.
True.
The problem was always human incentives. Product managers want features shipped today, you know? They don't care about a runbook that might be used next year. Writing all this operability proof took days of human engineering time, so it was always skipped. What fundamentally changes this dynamic now?
What changes the dynamic is the absolute collapse of the cost of creation. Yes. Before, building out chaos tests and saturation limits was an expensive human bottleneck. Now, AI agents make drafting this entire operability package incredibly cheap. The agent can write the runbook, define the SLOs, and generate the latency injection experiments right alongside the feature code, literally in seconds.
Wow, so the economic excuse just evaporates.
Completely.
Because the AI makes it practically free in terms of time to generate the safety equipment, its absence is now totally indefensible. You have no excuse not to require it at the merge gate.
The bottleneck has shifted. We've gone from the hard part being writing the code to the hard part being proving the code.
But even with all these strict pipeline rules, we are still dealing with an entity that doesn't sleep. I mean, an AI agent can write and submit code 24 hours a day, 7 days a week. We have the rules of the road defined, but how do we actually enforce a speed limit on a machine that can output infinite code?
To enforce a speed limit, we first need telemetry. We need actual data, not just anecdotes about AI being fast or buggy. The author argues we must add one new mandatory form field to every single incident review going forward.
And that is
tagging agent involvement. We have to document whether the failing code was human-written, agent-assisted, or agent primary.
Oh man, I can hear engineering managers groaning right now. Developers absolutely hate filling out post-incident forms. When the fire is out, they want to go back to sleep, not do data entry. How do we ensure that data is actually reliable and useful?
You enforce it because it is the only way to measure comprehension debt. We need to statistically track if agent-heavy code fails in fundamentally different ways than human code. And more importantly, we need to know if it takes human responders significantly longer to recover from agent primary outages because they lack that mental map.
Right.
You cannot manage a speed limit if you aren't measuring the accidents.
So how fast should we actually allow these agents to go? Once we have that data and we can clearly see the impact of AI-generated code on our incident response times, how do we actually throttle the AI?
The answer is remarkably objective, and it brings us right back to the error budgets we defined in the service contract.
Oh, interesting.
The author's philosophy here is brilliant. You do not need to invent a new morality or a new set of ethical rules just for machine-written code. You trust the gate, not the actor.
Meaning we evaluate the output, completely ignoring who or what typed the keystrokes.
Exactly. We shouldn't care if a 10-year senior engineer wrote the code or an LLM wrote the code. We apply the exact same service policy regardless. If a service is burning through its error budget too fast, meaning the code being merged is causing too many minor incidents, degrading the user experience, or triggering the pager too often, the system mechanically tightens the policy.
So it acts as an automated governor.
Yes.
If the AI agent's code is unstable, it loses its license to drive fast. You freeze non-remediation changes. You cap the number of automated pull requests allowed per day, or you suddenly require multiple layers of manual human review before anything can merge.
If we connect this to the bigger picture of system architecture, A service only earns its high-throughput velocity by actively demonstrating that it can absorb and recover from the changes it ships. Agents should be allowed to go exactly as fast as the service can absorb without missing its reliability targets.
And not a single bit faster.
Right. They should not be allowed to merge one single commit faster than that.
A testing gate only proves that a predefined standard ran successfully. The pager is what proves whether you can actually live with what slipped through. That is the core reality check of this entire source material.
It really is the ultimate test.
Yes. We have to stop assuming that passing unit tests means a system is safe to operate in the real world. We are currently letting AI write our digital infrastructure at an unprecedented lightning speed, but we are the human beings who have to live in it, maintain it, and rebuild it when the lights go out.
And if we don't force the AI to mechanically prove that its systems are operable and understandable by humans, we aren't engineering the future. We are just building a massive, highly efficient house of cards. The hidden cost of comprehension debt will entirely bankrupt our engineering teams the exact moment a truly complex crisis hits.
So what does this all mean for you? If you are listening to this and you run a team, it means taking a hard, immediate look at your deployment pipelines. Are you just testing for functionality, making sure the code does what the spec says in a sterile room? Or are you actively testing for operability, forcing the system to prove it can survive real-world degradation?
Are you just generating confidence, or are you demanding proof?
Exactly. But I want to leave you with one final, slightly chilling thought to mull over. One that stretches just beyond today's capabilities. We have spent this entire time talking about the human holding the pager at 3 a.m., overwhelmed by the comprehension debt created by the machine.
Yeah.
But AI is advancing incredibly fast. What happens a few years from now when the agents become so sophisticated that they not only write the feature code and the run books, but they are also given access to production to answer the 3 a.m. pages?
Oh, wow.
Right. What happens when they are trusted to fix their own confident defects in real time? If we cross that threshold, our human comprehension debt will eventually reach 100%. We will have completely and voluntarily surrendered the mental map of our own digital infrastructure to the machines. And if we do that, what happens the day the agent itself goes down?
That is a terrifying question.
Think about it. We'll catch you on the next deep dive.